Dimension of basic physical quantities in science and maths from 11 years old above. SI unit stands for International System of Units. Website for this address is this. The acronym here is National Institute of Standard Technology. HTTPS stands for Hypertext Transfer Protocol. Protocol stands for rules, and S for secure. www stands for World Wide Web. There are 7 days in a week. There are 7 basic XI units. The first one is mass, length, time, electric current, temperature, amount of substance, luminous intensity, that's intensity of light. The quantity symbol is M for mass, length is X or L or S, time is T, current is I or lowercase I, temperature is capital T, and amount of substance is lowercase n. Luminous intensity is capital I subscript V. The dimension symbol is capital M for mass, capital L for length, capital T for time, capital I for current, theta, this is theta for temperature, N, capital N for substance, amount of substance, capital J for luminous intensity, that's intensity of light. The unit for mass is kilogram, kg. Unit for length is meters, m. Unit for time is seconds, s. Unit for current is ampere, capital A. Capital K for mole, mol. Candela, cd. Talk about. So we got script. This one is superscript M. That means Superman flying or Superwoman flying. In maths, it's called power, exponent, index. That's what you call that in maths. And if it's underneath, this one is subscript, like submarine underwater. So if you write x squared, that's the exponent is 2, and the base is x. Here, H2, 2 is subscript, x squared, 2 is superscript or power. We need to know indices as well. Anything to power 1 is anything. S to power 1 is S. T to power 1 is T. James to power 1 is James. Number 2 of indices. Anything to power 0 is 1. S to power 0 is 1. T to power 0 is 1. James to power 0 is 1 in maths. 1 over anything is anything to power minus 1. 1 over S to power 1 is S to power minus 1. It's that 1. Let's go there. 1 over S to power minus 1 is S to power 1. So we can swap this with that. That goes there and that one goes there. So basically we're swapping. 1 over x squared is x to power minus 2. You can see, and also we can swap that. 1 over x to power minus 2 is x squared. 1 over t cubed is t to power minus 3. 1 over t to power minus 3 is t cubed. Another thing to remember is formula. A equals b over c can be written as b times 1 over c, which equals b times c to power minus 1, and therefore b c to power minus 1. So that's what that is equal to. So we should be able to transform that equation to b c to power minus 1. Again, these are the 7 basic units. So now we're going to start with 1, maths. Number 1, mass. As you can see, mass, if we write in the basic unit for mass, mass is, that's M for mass, so you got mass there. Length, we don't have length. Do we have time? That's 0. Do we have temperature? That's 0. Do we have current? That's 0. Do we have amount, mole? That's 0. And do we have intensity? That's 0. So we can see 0, L to power 0 is 1. So this will be M to power 1 times 1 times 1 times 1 times 1. This is 1, 1, 1, 1, 1. Because anything to power 0 is 1. So if you times it by all by 1, it will be 1. So 1 times that will be that, which means that would be equal to that's capital M, by the way, and that equals kilogram for mass. So the unit here is kilogram. So we can see unit, and here is dimension. For mass, dimension is M. We use square bracket for dimension, and for unit it's kilogram. Number 2, length. So for length, we have no mass, length is only 1, time is 0, temperature is 0, current is 0, number of amount of substance is 0, and intensity is 0. Don't forget, this is 1. M to power 0 is 1. T to power 0 is 1. So finally, we have L to power 1, which is basically L. And the unit for L is in meters. So L can be in meters or centimeters or decimeters. And so we can say this is unit and this is dimension. So dimension and unit. For time, we draw a square bracket as well. M is 0, L is 0, time is 1, angle and theta, temperature is 0, current is 0, N, which is amount of substance, mole, 0, and intensity of light is 0. Anything to power 0 is 1. Therefore, we have time, which basically is time, and time is seconds. So we can see this is unit and this one is dimension. Four, area. Area is length times breadth, but this is area of a square. So area of a square can be L times L, and that is L squared. So what do we have? Do we have M? M is 0, L is 2, and I put 2 there. Time is 0, temperature is 0, current is 0, N for mole, that's 0, and J for intensity, 0. So what do we have left? We have L, that is meter squared. Or if you use centimeter, that would be centimeter squared. Or if you use decimeter, that would be decimeter squared. Number 5, we're looking at volume. If you have a volume of a square, you draw a square. Let's assume that's a square. And a square will have a height of L, a length of L, and a breadth of L. So the volume of a square will be L times L times L, and that will be L cubed, because that's L to power 1, L to power 1, L to power 1. We add the power when we're multiplying same base, so that's L cubed. Now we need to write the dimension, which is, do we have the mass here? No. Do we have the length? Yes, 3. Do we have the time? No. Do we have the temperature? No. Do we have the current? No. Do we have the mole? No. Do we have the intensity? No. Don't forget, anything to power 0 is 1. So we are multiplying all these together. So we're going to get L cubed. So that's 1, because anything to power 0 is 1. 1 times L cubed is L cubed, times T to power 0, which is 1, times Q to power, theta to power 0, which is 1, times I to power 0, which is 1, times N to power 0, which is 1, times J to power 0, which is 1. So 1 times L cubed is L cubed. Unit will be meter cube, or if you're using centimeter, that will be centimeter cube, or if you're using decimeter, that will be decimeter cube. Number 6, density. Density is mass over volume, and therefore we can write mass times 1 over volume. But we know what volume is, so that will be mass times 1 over length times length times length. And that equals mass is capital M for dimension times 1 over L cube. and that will become ml to the power minus 3. So for dimension, it's going to be square bracket ml to the power minus 3, and the unit will be kilogram meters per cube. Or you might use kilogram per decimeter cube, or you might use kilogram per centimeter cube. So this is unit. Number 7, speed. So speed equals distance over time, and we can split that up as distance times 1 over time, which meant distance is length, so that's L times 1 over T. I can see L and T involved, and that can be L T to the power minus 1, which is length to the power 1 time to the power minus 1, and that can be length and time to the power minus 1, close bracket, and that equals meters per second or meters over seconds. So this is unit here, and here is dimension. So this is a dimension for speed, and that is unit for speed. Number 8, velocity equals displacement over time, or you might say change in displacement over change in time, which would then give you displacement over time times 1 over time. But we know that displacement is length, so that's length times 1 over time, and that will be length time to the power minus 1. Put it in square bracket, and that equals meters per second. Per means divide, or you might say meters per second. Displacement and distance are similar in unit, but they're different because distance is scalar, and scalar has only size. Some size is also called magnitude. But displacement is vector, and vector is size plus direction. So if I have a displacement of a distance of 2 meters, the displacement will be minus 2 meters or plus 2 meters or 2 meters north, or you might say 2 meters south. That's what you called vector. Vector is showing direction and size. Direction is negative here, direction is positive here, direction is south, north, east, and west. Whereas distance is only showing size. Number 9, acceleration. Acceleration is change in velocity over change in time. If you have change in velocity, then you're going to get a velocity. If you have change in time, then you get a change in time. So acceleration is velocity over time. And that can be separated as velocity times 1 over time, as you can see. But also, what is velocity? Velocity is displacement over time times 1 over time. As a result, we can split the displacement over time. So that's displacement times 1 over time times 1 over time. And that is displacement is L, and times 1 over time times 1 over time. And that is L times 1 over T squared, which will be equal to L T to the power minus 2 in dimension, and that equals to, in unit, meters per second squared, or you might write meters over second squared. So you can see this is the unit, and that's dimension. Number 10, force equals mass times acceleration, and that equals ma. So what we can do now is to say, well, that's mass times acceleration is velocity over time, by saying mass times velocity times 1 over time. And now we can write velocity itself, mass times displacement over time. That's what velocity is. Then times 1 over time. Finally, we can say this is mass L times 1 over time squared. As you can see, this is time at the bottom, so that's time squared. And that will give m, square bracket for dimension, L, T to the power minus 2, close bracket, and that equals kilogram meters per second squared. or you might write kilogram meters over second squared. So you can see this is unit and this is dimension. Pressure is force over area, which equals to force times 1 over area. We know what force is. Force is mass times acceleration, and then we times it by 1 over area. But we know what acceleration is. So that would be mass times acceleration is displacement over time squared, because we've done it twice now. So acceleration is displacement over time squared, because it's velocity over time, and then velocity is displacement over time. So you're going to get displacement over time squared times 1 over area. So we got a mass now, right, times displacement, right, over t squared times 1 over area, which is L squared. So we can see displacement, 1L in the numerator, cancel the L in the denominator, and that gives us M over L t squared. And if we put that into square bracket, that will be M, L to minus 1, t to minus 2, close square bracket, and that would be, the unit now would be kilogram per meter per second squared, and that's pressure. And this is called Pascal, and Pascal has a symbol of PA. So that's what we call Pascal. So we got unit here, and we got dimension. We did force before, earlier. That force, that's the unit of force, and that's the dimension of force. That unit of force is also called Newton, and has a symbol N. Sorry, kilogram meter per second squared. Kilogram meter per second squared is called newtons. So that unit is called Newton. Number 12, momentum. Momentum is mass times velocity. So we can then say mass times displacement over time, and that becomes mass times displacement times 1 over time. And then we can finish that off by saying that's capital M for mass, displacement is length, and 1 over time. And that equals mass, length, time to power minus 1, square bracket, and the unit will be kilogram meters per second. So we can see the units there, and we can see the dimension unit. Number 13, impulse equals force times time. So now we need to write what force is, and that is mass times acceleration times time. So that meant impulse is mass times acceleration is velocity over time times time. So we can see acceleration here is velocity over time. Now time will cancel time because that's over 1. And so we're going to get mass times velocity, which is equal to, open square bracket, mass, displacement, time to power minus 1, close square bracket, and that equals kilogram meters per second, or you might say kilogram meters over seconds. So this is dimension, and that's unit. This unit is also called Newton's seconds, because momentum is mass times velocity, which is equal to force times time, which is, they have the same unit. Momentum and impulse have the same unit, and their unit is Newton's seconds. Number 14, energy equals work done, which is equal to ability to do work. We can define energy as force times distance or displacement. So therefore, energy is mass times acceleration times displacement. Mass times velocity over time, and then times displacement. But if we rewrite that one as mass times velocity, then times displacement over time. What is displacement over time? That's velocity. So that equals mass, velocity times velocity, which is mv squared. And that can be written as mc squared. So energy of Einstein is E equals mc squared, where C is equal to V. So to carry on with energy equals mv squared. But we know what V is. V, so that's m. V is displacement, which is L over time, and I'll square it. So I'm just squaring that. And that equals m L squared over T squared, because that's to power 1. So I times that with that, and that's to power 1, and I times that with that. And so I'm going to get mass L squared T to power minus 2. So for dimension, open the square bracket, m L squared T to power minus 2, close bracket. And the unit will be kilogram for mass, meters squared for length, and per second squared for time. Or you might write it as kilogram meter squared over second squared. And because that unit is called joules. J for joules. So the dimension for energy is m L squared T to power minus 2, close bracket, and the unit is kilogram meter squared per second squared. So that's unit, and this is dimension. Kinetic energy equals a half mv squared, and therefore we know that mv squared is energy, so that equals a half energy. And we just derived the dimension for energy, and that's a half square bracket m L squared T to power minus 2, close bracket. A half is not a dimension, so it's a constant. So the dimension is going to be m L squared T to power minus 2. That's from energy, which is derived in number 14. And then that will give us the unit. It's kilogram meter squared per second squared. And we call that joules. So this is unit, and that is dimension. Potential energy, and that equals mgh. If you have a mass, and that mass has a weight of mg, g is acceleration due to gravity, and the h is if you raise the mass by a height h, you've done a work. Work done is force times distance, and the force times distance is F times h. So the work done is force times displacement, and that is force is mass times acceleration due to gravity times the displacement. So you can see the force is mass times acceleration due to gravity, and that the mass times acceleration times displacement. And we know what acceleration is. Acceleration is velocity over time. So the mass times velocity over time times displacement. But that is mass times velocity times displacement over time. I just moved that time to there. It's the same time. And what does that give me? Well, that gives me mass times the velocity times the velocity. And that becomes mass times velocity squared, which is mc squared again. So the mgh is now mc squared, and that's the unit for energy as well. And I know what mc squared is from what we did last. So potential energy, we said, is mgh, and we proved that to be mc squared. And we know what c is. C equals displacement L over time. And if I want to do c squared, that would be L over time squared, which is L squared over time squared. Don't forget L is displacement. So I can put it here. M for mass, capital M for mass, for dimension. L, right, squared, t to the power minus 2. So that will be my dimension. And the dimension is square bracket, capital M, L squared, t to the power minus 2. That's a unit dimension of energy. And that will become kilogram meter squared per second squared. That's the unit of energy. So we can say unit and dimension. So the potential energy has the dimension of energy and unit of energy. And that is, the unit is in joules. Number 17, power is energy over time. And that equals work done over time. And therefore, work done is force times displacement over time. But what is force? Force is mass times acceleration times displacement, energy now, for power now, over time. But we know what acceleration is. Acceleration is displacement over time squared, and then times displacement over time altogether for power. The acceleration is displacement over time squared because acceleration is velocity over time, and then velocity is displacement over time. So that would be displacement over time squared. So now we can write the dimension, capital M for mass, displacement will be L squared, time squared, and time will be t to the power minus 3. And therefore, that should be equal to kilogram meter squared and seconds to the power minus 3. Just remember that that is basically, let me just undo that one here. That is times. So that is basically equal to mass times displacement. So let's use S for displacement squared over t cubed. And that's how I was able to get mass, which is that mass, because that's displacement squared. Displacement is S, that's S. And t to the power 2 and t to the power 1, that's t to the power 3 in the denominator. And that's why I was able to get this. And so now we got the unit and dimension for power. Number 18, frequency equals 1 over time. And that gives us a dimension of time to the power minus 1, because 1 over time is basically 1 over capital T, which is t to the power minus 1. And the unit is seconds to the power minus 1. But 1 over seconds, the unit is called hertz, which is Hz, and that's the unit for frequency. Unit for frequency is 1 over seconds, or seconds to the power minus 1. So the dimension is t to the power minus 1, and the unit is seconds to the power minus 1. And that's unit, and this is dimension. Number 19 is wavelength. And wavelength is basically length of a complete wave cycle. And if you draw a wave cycle, it goes from top to there, and that length from there to there is called lambda. So wavelength is lambda for the symbol of wavelength. The symbol for wavelength is lambda. The dimension is length, and the unit is meters. So that's unit, and this is dimension. 20. Stress is force over area, and that equals to mass times acceleration over area. So we can say mass times displacement over time squared, because that's what acceleration is, times 1 over length squared. That's area. Area is length squared. But displacement is length. So we can put a dimension in, capital M for mass, L for displacement, over T squared for time, L squared for area. 1L in the numerator cancels 1L in the denominator. So we're going to get M over T squared L. So we can say for the dimension M, L2 minus 1, T minus 2. And the unit will be kilogram per meter per second squared. So that's unit and dimension. Number 21, strain. Strain is equal to change in length over original length. And that is change in x over x, or you might say change in s over s, or you might say change in L over L. If you put in dimension for this one, dimension of change in L is going to be L, and then a dimension of L is going to be L. So the dimension of x, the length, is L, and the dimension of original length is L. But both cancel each other to give 1. So we can say no dimension and no unit, because it is a ratio of length, and the length cancel out. 22. Specific heat capacity is the energy required to raise the temperature of 1 kilogram mass of a substance by 1 degree Kelvin, by 1 Kelvin. And Q is the energy equals the mass of the substance times the specific heat capacity, which is C, times change in temperature. And to find specific heat capacity, I need to divide that by mass, I need to divide that by change in temperature, and I need to divide on the left hand side by both mass and change in temperature. And therefore, why did I do that? Because the mass will cancel mass, change in temperature will cancel change in temperature, and therefore I'm going to be left with C, and that equals Q, the energy over mass times change in temperature. And the dimension for energy, we know what that is mass times meter squared, temperature to power minus 2. And for mass, it's going to be mass in the denominator, and Q, change in temperature. So you can see Q here. So we go Q there, so it would be in the denominator there. So we go Q. So we can say C equals L squared T to power minus 2 to power minus 1. And that will be the dimension of specific capacity. And the unit for specific capacity will be meter squared per second squared per Kelvin. So we've got the unit and we've got dimension.